you very much, Mr. Shah, and thank you very much to all the panelists who spoke before me. And it's quite interesting that there's a lot of link in whatever topics, whatever things that I'm going to be talking. And especially Dr. Rajaram, who spoke before me, has already covered quite a bit on the catalytic aspects. So I'm going to look at more on the practical aspects and how we can bring it to the industry. So as a quick introduction, as momentum picks up in the decarbonization efforts across the globe, the focus on carbon capture, utilization, and storage becomes imminent and inevitable. The decarbonization efforts are challenging due to the different needs and aspirations of the government and private sector holders, as well as the geographical locations, project delivery risks, operational complexities, and limited technology advances. The implementation of any kind of decarbonization project is inherently complex, particularly in striking a balance between the cost, the revenue, and the value. In many cases, while the capital and operating cost is high and the revenue is apparently low, the improvement in performance can offset the expense and boost the overall value. Therefore, enabling the successful realization of CCUS, and in particular CCU projects, requires an innovative combination of existing practices and creative engineering designs that will create an effective production facility. Now, I choose the topic putting the U in CCUS because carbon capture and storage has been spoken about a lot in various conferences, and it has already been in practice for many decades. And there are carbon tax credits, there are benefits, there are funds that are being granted for all the CCS projects. But the CCU, when it comes to carbon capture and utilization, I'm sure many of you will agree that there are not many grants, there are not many funding that is available for these kind of projects. So that's why I come to the main topic of putting the U in the CCUS. So now, a quick agenda. I'll give a very short introduction of our company, Technip Energies, and why energy transition is our business. And within the energy transition as our business, what we offer in decarbonization. So that will be, I will keep it very, very short in the interest of time, because I know we are already running short of time. And I'll straight go to the case study of converting CO2 to methanol and CO2 to calcium carbonate, which is pretty much similar to what my previous speakers have told, and what we have in conclusion. Now, Technip Energies at a glance, as most of you would have known, the name keeps changing, but the prefix Technip remains the same. And we are still the same. Everybody is, the management, the staff, we are still the same. We are a leading project engineering and technology company listed in Euronext, and with more than 25 leading proprietary technologies, both owned technologies as well as technologies through alliance or exclusive agreements. We have 450 projects in execution, and most importantly, energy transition becomes the core of our business since last year. The world is moving towards energy transition, and that's where we also are pretty interested in that. So now, energy transition as our business is a 4-pillar framework, covering the 4 main pillars are looking at LNG, sustainable chemistry, decarbonization, and carbon-free energy solutions. So basically, in sustainable energy, everybody knows, so I'm not going to dwell on it. Sustainable chemistry is all about the biofuels, biochemicals, circular economy, recycling plastics, where we have our own technology. And we also have alliances, and we have been in this business for more than 3 decades. Decarbonization through energy efficiency improvement, blue hydrogen, we have proprietary technologies for that, carbon capture, utilization, and storage. And carbon-free energy solutions basically covers green hydrogen, offshore wind, solar, and nuclear. So basically, we are feedstock agnostic, we are technology-driven, and we have an exceptional execution given our 6 decades of project delivery experience in the hydrocarbon industry. So moving on, in terms of the accelerating the energy transition, three main areas where we look at hydrogen, sustainable chemistry, and CO2 management. And today's topic is all about CO2 management. So without dwelling much into this, because I don't want to be taking too much of on the meeting time, on the conference time, so I'd go straight what we have to offer in decarbonization. So basically, the main areas we concentrate on decarbonization is improving the energy efficiency, because energy efficiency improvement has been spoken about. Many companies have already done it, and now the new era of energy efficiency improvement is all about digitalization and going to the level of molecule to see where the fuel is being lost and how to recover it or how to minimize the consumptions. Carbon capture, utilization, and storage, that is the topic of today's discussion. Blue hydrogen is same as SMR, a fossil-based hydrogen with carbon capture and storage. That's blue hydrogen, and I'm sure many of you would have seen in LinkedIn that we have our own proprietary technologies. And we also provide advisory services on carbon assessment and carbon management. So in terms of differentiators, we are a technology-centered company. We are not just an EPC contractor. We are also a technology-focused company, and we have integrated solution across the CCUS chain. And we have tremendous amount of investments in research and development and co-development capabilities. And we have proven technology experience and EPC execution. So basically, the intention here is that we are just not a research company or a technology company. We're also an EPC contractor. So EPC contractor working with a licensor mindset or a licensor working with an EPC mindset. Both ways we can take it, and that is where we bring benefits to the clients. So summarizing all those things in one shot, digital advisory services, we spoke about it. Energy efficiency, we spoke about it. Now in terms of technology portfolio, we have an exclusive alliance with Shell Consol. Host technologies, that could be a lot of similarities with the KM-CDR that Takeshi-san presented. And we also have the CCUS technologies and our own patented processes for that, which is called the 10 Offshore Sea Hub. So today I'm not going to be talking about it because I'm more on the case study of CO2 to methanol and CO2 to carbonates. Now in terms of CO2 utilization, so it's just a short video. Okay, I hope you found that interesting. Sorry for that. Okay, so I'll quickly jump into the case study for what we perform for a national oil company in Southeast Asia. Due to confidentiality agreements that we have with the client, I'll not be able to disclose the name of the client, and not much of details about the project, but at least I can present about the technicalities of the project. So this plant is supposed to be located in Thailand, and the design basis considered a methanol production of 80,000 tons per annum and calcium carbonate or aggregates production of 60,000 tons. So on this basis, we set out to do a case study for this client and coming up with the what are the type of technologies that are available, what does it cost to do this plant, what is the kind of plot plan that will be required, what are the challenges that the client will be facing when they have to develop this into a project. So basically, this is completely different from the challenges from what Dr. Rajaram and Dr. Gaurav have presented before. Now, in terms of methanol and methanol from CO2 and hydrogen, the traditional syngas route, as everybody know, is syngas plus hydrogen gives methanol, which is an exothermic reaction. And the CO2 to methanol route is also exothermic, but you can see the difference in the heat there. And there is also the reverse water gas shift in the traditional syngas route, which is a CO2 plus H2 giving CO plus H2, H2O. Now, the major difference that you would see here, the crude methanol quality in the syngas route, the traditional syngas route is about 10 to 15% water, and the CO2 to methanol route contains about 35% water. So the catalyst is the catalyst selection and the catalyst activity has to be is very sensitive to this water, and it has to be carefully selected. Now, the side reaction products in a traditional syngas route is higher alcohols, oxygenates, and hydrocarbon, which makes the purification process a bit complicated. Whereas in the CO2 to methanol route, it is very limited side reaction product components, and the distillation process for methanol purification is quite simple. Now, between the traditional syngas route and the CO2 to methanol route, what we find as similarities is the synthesis reactor operating conditions at about 80 bar to 40 to 50 degrees C, which pretty much matches with what Dr. Rajaram was presenting before. Thank you, Dr. Rajaram, for bringing out those details so that I don't have to spend too much time here. And the copper zinc oxide catalyst, which is also, Dr. Rajaram had gone very much in detail. Much appreciated. So in the next slide, what we see here is CO2 and hydrogen as a feedstock purification. We'll go through the steps in a block flow diagram. And then CO2 and hydrogen are mixed and compressed methanol synthesis in the synthesis loop, and methanol purification by distillation. There are several possibilities for the distillation. It can be a two-column system, it can be a single column system, depending on how we balance between the capital cost and the operating cost, and the associated utilities that are required. Now, the main parameter is for a methanol production of 240 tons per day. The CO2 required would be about 360 tons per day, and the hydrogen required is about 24 tons per day. Now, let us say we want to produce this hydrogen from a green hydrogen facility to make it a green methanol plant. Then, as discussed in the previous session, I don't know how many of you have followed the previous session. One of the challenges that was discussed in the previous session was all about how do we manage this hydrogen production through electrochemical storage? How do we manage batteries? And how do we ensure that it is available continuously? So in this case, I'm assuming that the hydrogen will be stored at something like 3.6 times what is required. So there is a calculation for that. I'm not going to go too much into details. And to produce 87 tons per day of hydrogen, we need approximately 200 megawatt of electrolysis power. So those are the things that are going to put some challenges on this entire scheme of things, which is also now this green hydrogen production adds to the capital cost nearly more than the double of what it takes to produce methanol. So this arrow that I show here is basically an option to manage the intermittency of the renewable power. Now, in the next slide, what we'll be seeing is the block flow diagram. So what you see here is a renewable power source that comes to a transformer. Okay, a renewable power source that comes to a transformer, and the transformer then sends the power to the electrolysis. We get CO2 from an external source, from a power plant or a process plant, send it through a purification process, and then bring it for methanol synthesis. Now, for the electrolysis production, we need demineralized water. So we take raw water with reagent chemicals, produce demineralized water, and the oxygen can be a byproduct here, which can be sold. That's pure oxygen, which can be even sold as medical grade after a little more, after final purification. And this methanol synthesis would be, because given the exothermic nature of the reaction, we produce a lot of steam. So it requires a steam system, and methanol, the produced methanol can go for storage and export. So now what we see here is there is a trade-off between power storage versus hydrogen storage, which is normally evaluated during a feasibility study, giving credit for the location where this project will be, and what are the availability of the sources of renewable power, and how close they want to go to calling it low carbon. Because in some places we cannot call it green essentially, but it could still be low carbon. If, let us say, we are reducing the carbon emissions by 50% of what is the industry standard. The typical plot arrangement, what we estimated was we'd have the hydrogen compressor, the CO2 compressor, the synthesis reactor. Now, what do you see here? Those who are familiar with the traditional syngas route, you would say that the plot area is quite big, because there is a reformer section where the hydrogen is sent to a reformer to produce the syngas, and then the syngas comes to the synthesis. Now, in this case, we don't have a reformer section, due to which the plant overall area reduces by more than a half. So if you see the overall ISBL area is only about 60 meters by 60 meters, whereas if you do a traditional syngas route, this is going to be at least 2 or even 3 times bigger than this. So those are the advantages that it comes with in having a CO2 to methanol production. Now, there is no showstopper. There are catalyst vendors, there are licenses available. Many catalysts, many types of catalysts are available. So there is no showstopper here. What is only important, or what is required, is the funding of these projects, and so that it can see a reality. Now, moving to the next slide. So the main challenges that we see here are basically technical challenges. Depending on the source of the feedstock of the CO2, if it contains sulfur, then there is a need for a sulfur guard bed, because the catalyst is quite sensitive. The same thing if it contains any unsaturated or olefinics, depending on the source from which it is coming. Then the feedstock compression, this would be again a matter of study, an engineering study would be required. A significant impact on if the feedstock is available at low pressure, because when we say low pressure, it's close to atmospheric. From there, it has to be compressed to about 80 bar. That's a syngas pressure, 80 or 85 bar. And the choice of compression machines, whether it's a reciprocating machine or a centrifugal machine, due to the size, and whether it can be joint or separated. So all these would require separate studies specific to the project. Now, in terms of design optimization, there are many areas where we can do the design optimization. I'm not going to go too much into the details in the interest of time, but as engineers, we all definitely understand these 3 bullet points. So basically what we can say is we don't see any major technical showstoppers in converting CO2 to methane. So only and whatever you see here as challenges, there are solutions for that specific to the location in which the project is being done. Now, the next case study is converting CO2 to calcium carbonate. So here, what we find is the CO2 purity is very dependent on the technology. So a purification step can be mandatory depending on what is the source and what is the type of mineral that is being used as a feedstock. So in the mineral feedstock, some residues are more reactive than others with CO2 and does not need additional ingredients, whereas some residues are less reactive. Therefore, what we have seen is all these technologies require a test phase